So today we are continuing with the stack problems. So today we are going to solve the stack problem, carpet and the largest rectangle in a histogram. Okay. So previously we solved these two problems in yesterday. So today we are going to try to solve these two problems, and then we will try to move on to the binary tree. But let's see how long it takes to solve these two problems. Then we'll think about those. Okay. So let's start a clock. Okay. Let's go through the problem and try to solve it in another 30 minutes. It's a car pit. There are n cars at given miles away from a starting mile 0, traveling to reach the mile target. There are n cars at given miles away from the starting mile 0, traveling to reach the mile target. You are given two integers array position and the speed, both of length n, where position I is the starting mile of an ith car and speed I is the speed of the ith car in miles per hour. Okay. A car cannot pass another car, but it can catch up and then travel next to it at the speed of slow car. A car fleet is a single car or a group of cars driving next to each other. Okay. A car fleet is a single car or a group of cars driving next to each other. Okay. The speed of the car fleet is the minimum speed of any car in the fleet. Okay. If a car catches up to a car fleet at a mile target, it will still be considered as a part of the car fleet. If car catches up to a car fleet at a mile target, it will still be considered as a part of a car fleet. Returns the number of car fleet that will arrive at the destination. Return the number of car fleet that will arrive at the destination. So let's start. So our target is 12. So positions are 10, 8, 0, 5, 3. And speeds are 2, 4, 1, 1, 3. Okay. So at speed 3, at output will be 3. So the car starting at 10, speed 2, and at speed 4 becomes a fleet, meeting each other at the 12th. Okay. The fleet forms at target 12. Car is starting at 0, speed 1, does not catch up to any other cars, so it is a fleet by itself. The car is starting at 5, speed 1, and 3, speed 1 becomes a fleet. So 3 at 3 speed, meeting each other at 6. Yeah, 5 will be 6 and this will be 6. So the fleet moves at the speed 1 until it reaches target. The fleet moves at speed 1 until it reaches target. Target 1, 3, 3 through speed target, so it will reach 3, 3, then 6, then 9, and then half a step in 1. There is only one car, but hence there is only one fleet. 400, 0 to 4, 4 to 1. Okay, so 0, 4, 8, 12, and so on. For 2, it will be 2, 4, okay, 2, 4. Then instead of at a 0 position, it will be 4, and the second position also will be 4. So both are the same. So they will become a fleet. Then for fourth position, fourth position, it will become it will have a speed of 5, so it will be 5. So then it will be 5, 6, 7, 8, 9, and then for these two 0 and second it will be 4, then it will move 6, 4, 6, 8, and for 4 it will be 6, then 7. The car starting at 0 speed and second speed fleet meeting each other at 4. The car starting at 4 speed travels to 5. Then the fleet of 4 speed 2 and the car at position 5 will become one fleet, meeting each other at 6. Meeting each other at 6. The fleet moves at the speed of 1 until it reaches the target. Location चलो पूछे the car starting at 5 speed 1 and 3 speed become a fleet, meeting each other at 6. The fleet move at speed 1 until it reaches. Okay. The starting car will become one fleet. Speed 0 does not catch up to the other is one fleet, and 10 and 8 will become one fleet. So 1, 2, and 3 fleet before reaching to 3. So before reaching 1, so this is also before reaching the 4, it will become 1. So how can we solve this problem? Okay, can we solve this problem? So what can we do? We'll move through the position equation and add speed. Okay, once we add the speed, like for the first iteration, this will be 12, this will be 12, this will be 1, this will be 6, this will be 6. Once we add up the speed for the first iteration, we'll again go through the positions and see if there are similar positions. Okay? So these two are similar, so what we do is we add those as a 1 unit. Okay, and so this will also be 6, and add these two as 1 unit and this as 1 unit. Okay, then again we keep on iterating till we go to 12. Okay, till we go to the 12. So this is already reached at 12, so we'll move on to this one. So this will be 2, then 3, then 4. Okay, so at last it will become 12. So it will for this fleet it will take almost 11 more iteration to reach the target. For these we can do is 9 and then 12. Okay, so we'll reach in third iteration. 2 more iteration will reach. For this we'll need to do 12 iteration and this for 1 iteration. Okay, then let's get another example. See if this is 12, but if there is a fleet but there is still an issue, like we still have an issue open. So we got this. And for this one, at the speed 3, it will be 3, 6, 9, and then 12. That will be greater than target. So we have already reached. Okay. But what if, like, let's say, let's say this one. What if, like, we get speed of 5, we have 1, and this 6, that is 3. So let's say it is 2. So 4, 5, 1, and 3, 2. So it will be 6, it will be 5. Then it will be 7. And this will also be 7. So we'll meet. What if there is a way to surpass it? Like if there's 5 and then 4, and this will go to 6, but this will go to directly 7. Then what? Like let's say it's 2, it's like 3, and that will be 1. So it will be, so let's just start with 2 and 1, and speed of 1 and speed of 3. So for 2 it will become 3, it will become 4. Okay. So as you see, like, for 3 we surpass it by moving past it, by moving by like 1, 2, then 3. Okay. So it's already 3, then it become 4. So does this should be a fleet. So that's the problem. Like if a car catch up to a fleet at a mile target, it will be considered as a part of a fleet. Okay. A car is a single car or a group of a car. A car fleet is a single car or group of a car driving next to each other. The speed of a car fleet is minimum. The speed of so how can we solve this problem? Think 12 for 113. So 10 plus 2. So if we add 10 plus 2, then 8 plus 4, then we are moving through this, moving through the equation. We'll see if there is any similarity. We pop that one. Stack sorting trick. Stack. So this is also a problem, similar problem to monotonic stack. Okay, monotonic stack is simply in ascending order. We stack in ascending order. So what it is, 10. It will be 12, then we'll have 12. It is in ascending order. So 12, 12. So we pop the 12, then we add 1. We leave the 1. then we add 5 and 1 6, so 6 is greater than this. So what we do is pop the 1, so we have 12 and 1, and for 6 and 6, so 6 6 we will have single, so 1 6 and 6, but we have popped ones. So what we do is one letter senior stop array stack sorting. So if we sort this based on position, so 0, then third, then simply position wise. So it will be 10th, 12th. Okay, so about sorting, we need to sort these also based on these. So let's say we sort these also based on these. Okay, what we'll do, sorting, we will have 1 1 6 6 12 and 12. Monotonic stack. So we have descending array 1 6 12 12. We compare. We see if then we add the slowest to the bottom of the stack, so that will be 1. Then we'll have 6 and 6, then we'll have 12 and 12. Okay, then again we'll move to the equation. If we reach this, so if we have 2 singular and reached the fleet, so it is so first draw a picture of all the points which represents the position and respective speed of a car. Let's first draw a picture of all the points which represents the position and respective speed of a car. It is appropriate to represent the position and the speed of each car as an array, where each cell corresponds to a car. It is also logical to sort this array based on the position in descending order. Because a car can only form a fleet with each other that is ahead of it. Okay. Sorting the array in descending order ensure that clarity about the final speed of each car. Sorting in ascending order would create ambiguity, as the next car might form a fleet without another car while reaching the target, making it difficult to determine the final speed. Calculate the time of a car to reach each of the target straightforward and can be done using a formula. Time is equal to target minus position divided with the speed. The time for a car to reach a target is straightforward and can be done using the formula. Now it's become easy to identify the two cars which will form the fleet if and only if the car ahead has a time that is greater than or equal to the time of the car behind it. Now it's become easy to identify that the car will form the fleet if and only if the car ahead has a time. Time greater than or equal to the time of the car behind it. So how can we maintain the total number of fleet happened while going through the area? Maybe a data structure will is helpful. So we can use a stack to maintain the time of a fleet, times of a fleet. As we iterate through the array, sorting in a descending order of a position, compute the time for each of the car to reach the target and check if it can form a fleet car ahead. If the car, if the current time, if the current car times is less than or equal to the top of the stack, if the current car time is less than or equal to the top of the stack, it becomes a same fleet. If the current car time is less than or equal to the top of the stack, it becomes it joins the same fleet. Otherwise, it forms a new fleet. We push its time to the stack. The length of the stack at the end represents the number of fleet formed. So what we do is first sort these in ascending order, and sort these also in ascending the sort these also based on these. Okay, so after sorting both of these, what we do is we calculate the time. So time will be for the position. What is the formula? Target, that is 10 minus position, 10 minus 4, that 10 minus 4, that is 6 divided by 2. So it will need 2 iteration. What it is? It's called paste. So what it is sort these. Okay, sorting it will be 0, 1, 4 and 7. For this it will be 1, 2, 2 and 1. So what it is, calculate the time from here to here. So for this time will be 10 minus 9, 10 minus 1 divide, so 10 minus 0 divided by 1. So for this it will be take 10 iteration. For this 10 minus 1, that is 9, 9 divided by 2, so that will be 4, 4 and half. So let's do it's a 5 iteration. Okay, and then for these it will be 10 minus 4, that is 6 divided by 2, that is 3. And for this it will be 10 minus 3, this is also. Now according to the hint, after creating the time position, we can use the stack to maintain the time of fleet. As we iterate through the array, sorted in descending order of a position, we compute the time for each of the car to reach the target and check if the car forms the fleet with car ahead. If the car's current car time is if current car time is less than or equal to, so let's say if you're computing this, so if for this speed, if it is less than or equal to this, this is less than or equal to this, if the current car time is less than or equal to the top of the stack, it joins the fleet. So this will join its fleet as let's say one, it will be 3, it will be 1, then this will be 5, then this will be 5, then this will be 1, then this will be 2, this will be, so this will not form a fleet top of the stack. With these it will be 4, 6, 4, then 6, this will be 8, this will be 9, this will be 8 and 9, this will be 4, 6, and then 8, that iteration this will be 9. For this it will be 3, 5 and 7. So the car starting at 4 and 7 becomes a fleet at position 10. So this will be like 6, 8, this will be 8, 9, and then this will become fleet at the end. So if this is less than or equal to, so it is less than or equal to, less than or equal to. If the current time, otherwise it will form new fleet and we push its time onto the stack. Otherwise it will form a new fleet. If it is less than or equal to the top, it joins the same fleet. Otherwise it forms the new fleet and we can push its time onto the stack. The length of the stack at the end represents the total number of fleet formed. And instead of, sorry, we add it in descending order, not ascending order. So it will be 7, 4, 1, then 0. So this will be 1, 2, 2, and 1. Okay, then we have created another stack. Start from this. This will be 3, then its top position. Then we'll calculate this. So for this one it's 3, so which is greater than or equal to 3. So we don't push it into the stack. We just move on to the next one. Then for this one, we again check 10 minus 1 9, 9 divided by this will be 5, so which is not less than or equal to this, so we push this into the stack. For this one, whatever it will be 0, so this will be 10, so 3. Okay, so let's do this. Okay, let's sort your position. So how before sorting, we need to sort these two both. If we sort it in say descending order, we don't know how to sort these. We need to sort both speed also in this ascending order, so we can calculate, or we can calculate it once. Like we calculate 4, this, then we have then we have a time. We have time of all of this. Then sort its time based on this. 4, what we'll do is, how can we do this? Like, I will sort these based on this. So for 0, it's 1. So it's index. So what will 0 become? 0 comes at 1. So we need to sort these both. So first what you do, we'll create, let's start on the 10 minutes. Okay. So what we do is we'll sort these both. Okay. Sort this, then we'll create, let's create a copy of this, then sort this. So let's create a copy vector int it position. Okay. Equal to it position. Okay. Then what it is, sort POSTN position, beginning of POSIT position dot end in greater. How do we do in greater? What is sort vector in C++ in descending order, that will be greater something like greater int function. Okay. So that is, copy this. Yes. So let's cut this. Paste this up. ATER greater function. Okay. With the greater function. Okay. Greater int. We have one sorted. Now what it is, instead of doing this, we'll create a hash map with its position. Okay, so for 0, its position is this, and we'll move through this. Let's create a hash map. Or DE ordered map and ORDE unordered map of int hash map. Let's do for each int I 0 less than POSIT and position that LZ is size I plus. So if you see the constraint position, all the position are unique. Okay, so we have I is equal to 0, position that size I plus plus. So what we do is simply we add position and its index. So simply let's hash map if, so we know that it will be none. So hash map POSIT and position I. Now we have, so we sort this, we have sort this, then we have sort these. So let's create a stack. Get a stack of int. Stack. Okay. Now for each int I is equal to 0. Sorry, I in set and position. Okay, POSIT and position. What it is, calculate time. So time time equal to, let's say time equal to, what it is, time equal to target minus I. Target minus I divided by divide by what is it? Target minus I, that is position, divided by speed. So speed, that will be speed. So that is speed of what is it? Hash map of I. Okay. So whatever the value of that position in hash map is, this. Okay. So now we will have speed, but we need this to be in what do you call arranged. Well, we need like 4.5, we need 5 instead of 4. So what do you call 1, 2 value return the upper bound if float. Okay, so how can I do this upper bound if it is float? So what we can do is denominator target minus, I think speed will be this, then what it is denominator divided by this, then math, that's seal. So perform true division, then seal, then perform true division. So we are already doing this, then sealing it. So we use function math dot in C++. So what is so target 10 I and speed is equal to 3. Target I speed, that's him. Get upper bound. Speed and action. Let's let a little bit complicated. Math to use a C function which computes the smallest integer value not less than the input. If you must stay in the integer arithmetic, you can calculate this string using a plus b minus 1 divided by b for positive integer a numerator and b denominator. So we can either use this formula or use this, then or use 7/3, that is 2.33, leading to the correct upper bound. Let's leave this for now. Let's leave this for now. Let's leave this upper bound problem for now. Let's see if ti time is, if it is less than or equal to s dot top, then we just, if it is less than, we will just continue and ti and you will continue. And else what it is, we push as the push time. So and we need to, before doing this, we need to check if it is empty or not. If this will be if as that empty, if it is not empty, if it is empty, that's so at the end we just return G1 return tested size. Let's see, okay, so we are getting 3. So for this we got the wrong answer, so we got it for this one, but we are not getting it for this one because I think it is 4 because of this time upper bound. Okay, so 4 we have 6 minus 10, that is 4. 4 divided by 3, that is 2. 1 point something, that will be 2. And for this 10, so now first we have 8, then 6. So for 8 we have 8, 10 minus 8, that is 2, divided by 2, that is 1 in one position. And for this 6, for 6 we have 10, this is 10 minus 6, 10 minus 6, that is 4. So 4 divided by 3, 4 divided by 3, that is 4 divided by 3, that is 1 point something. So this is also 1. So output is 1, but we need 2 because both are different plate, because 4 divided by 2, that is 2. So this will do in 1, this needs to do in 2. So we need to make it upper bound. So let's do int nom nominator, that is target minus I, then int dominator, that is speed, that's I, then what it is we do this, okay, a plus b minus 1, so that is simply a is nominator, b is denominator. So a plus nom plus dom minus 1 divided by dom. So let's run this again. And now we are getting upper bound. Again we have issue, output is 2, we need 6. Compute this like we sort it like 8 7 6. For 8 8 minus 4 is 4, it will do in 1. 7, this will also do in 1. 6 also do in 1. 3, 10 minus 3, 10 minus, so 1 2 8 7 and 6 will be in one fleet, because in one attempt they will reach, okay, the target. For 3, that is 7. 7 divided by 4, that will be 7 divided by 4. 7 divided by 4, that is 2. Okay, so 2. And then for 3, then for 5, then we calculate for 5. 5, it's also 2. For 5, it's 2. 4, 4, it is 4, that is 10 minus 4, that is 6. The 6 of there is also 2. And for 3, 7, 4, it is also 3. So why it is 6 fleet? It should be 2 fleet. According to the previous the logic that I understand from the hint provided, it should be 6. So what's the issue? Let's copy, let's go to the chat. Let's add this. So what's the issue? Your implementation will be quite solid and closely optimal approach. Let's move on to the what's good and what can be improved and clear version. So position index using another map so you can access the speed or what your code does, right? Code does algorithm. You saw the position in descending order, that is right. You compute the time to reach. Okay, that is right. Okay, we can use this. Okay. You use a stack to track the fleet. Okay, if the current car reaches the similar earlier or same speed, it joins the fleet ahead. Otherwise, it forms a new fleet. It is exactly the correct logic. Issue is these are okay. So this you are using this. So we need to use this. Let's copy. Let's paste it here. Let's comment this. Let's use this test case. So that's in I then check target. It should be I. And now we are getting it. Still, we are getting an error 4.2. We are getting output as 1. For this 06, we are getting output as 1. So using this target minus position, that is CI divided by speed. You can use a stack to track the fleet. If the current car reaches the earlier or same speed, it's join fleet ahead. Otherwise, it forms a new fleet. This is the correct logic. So this is an issue. Unnecessary has map. You do not actually need this. Instead, you need to store position, time together and sort once. Stack is optional. You only need. I also thought of this one, but I told you that we can sort the position and get that. First get the time. After getting the time, we can sort the position and time together. So you only need to track the fleet time, not the full stack. So what we do is position, then we create this. So first what we're doing is calculating the time for each, then we're sorting car, okay, based on int, then we have fleet and double last. So we car, if car the second is greater than last. So in this, we are not even using stack. We do not even need a stack in this part. And in this, if we do like this, we do not need even stack than last time. Further than last time. Create plus plus, and last time is get further second. So let's go through the solution. Using stack. We can do this, but this solution is not even using stack.
Everyone, welcome back, and let's write some more NeetCode today. So today let's solve the problem car fleet. I think a lot of people don't end up solving this problem, but I think it's a very good problem and interesting problem to solve. So we're given n cars that are traveling along the same road. It has one lane. The road has only a single lane, and this is important for the rest of the problem. All the cars are traveling towards some destination which is at some target position, right? And every car that we're given has a position and it has a speed associated with it. And remember, they're all traveling in the same direction towards the target. And the position and speed are given in their own arrays. So there's two separate arrays given for each of these. And the important thing is that a car can never pass another car. That's because we have one lane in the road, right? So imagine we have two cars like these. This one's traveling and then this one's traveling, right? Let's say this one's traveling at 10 miles per hour and the other one is traveling 20 miles per hour. Of course, the faster one is eventually going to catch up to the slower one. But since they're in the same road, even when they do catch up, that faster one is just going to be traveling right next to the slower one, right? So the slower one was traveling at 10. Once the fast one catches up, its speed is going to be reduced to 10 because it can't pass the one that's ahead of it. So once cars are basically traveling right next to each other, that is called a car fleet. And by the way, if these cars are right next to each other, they're basically assumed to have the same exact position. Even though technically one is behind the other one, they still are considered to have the same position. That's what they mention right here. And they also mention a car fleet is just some non-empty set of cars that are basically at the same position, traveling at the same speed. And by the way, even a single car can be considered a car fleet. And the last edge case you might be wondering is what if a car catches up right at the moment that they both arrive at the destination point? Because remember, once they arrive at the destination, they're going to stop. So what if a car catches up exactly at the destination? Well, they're considered a car fleet. And what we want to do is determine the total number of car fleets that will arrive at the destination. So, in this case, for example, this example problem, we're given 5 cars, right? So initially we have 5 car fleets, but when they actually arrive at the destination, which in this case is at position 12, then they are going to be reduced down to 3 car fleets. Okay, so now let's try to figure out how we can actually solve this problem. Let's take a look at our own example. So here you can see I'm basically combining the two arrays that they give us. I know they give us a separate array for position and speed, but I'm just going to combine it into an array of pairs. So this pair represents, the first is the position, next is the speed. So this is at position 3 with speed 3. This is at position 5 with speed 2. This is at position 7 with speed 1. And our target in this case is 10. So I'm going to actually explain this problem in a way that you might not expect, because when you actually think about what these cars are, they're literally just a system of linear equations, right? We have the time on one axis, and we have the position on another axis, right? And if we take a single example such as this one, right, it starts at position 3. So position 3 is over here on the chart, and it has a speed of 3. What does the speed mean? It means that the slope is going to be 3, right? So every unit of time that passes, it will be in 3 positions ahead, right? So in 1 second, it'll be at position 6. In 2 seconds, it'll be at position 9. Excuse my kind of bad drawing here. And then at time 3, it'll be at position 12. So basically it reaches the destination 10, right? Remember, 10 is our destination. It reaches it at, let's say, 2 point something seconds, right? And we could calculate that if we really want to pretty easily. It's just a linear equation, but I'm just drawing it out just so you kind of get an idea of what's going on here. So now let's do this one, 7, 1, and let's use a different color just to kind of illustrate things. So it starts at position 7, and it has a slope of 1. So each unit of time is just going to go up 1 position. So at time 3 is when it's going to reach the destination, right? So we can draw a line like this one. And what you can already tell from this drawing is these intersect here, right? They intersect before they reach the destination. What does that tell us? That tells us that they are going to become a car fleet. This orange one and the blue one, right? They intersected over here before the orange one reached the destination over here. So what's actually going to happen with this orange one, this part of the drawing is not going to happen, right? because once they do intersect over here, the orange one is going to travel at the same speed as the blue one because it can't pass the blue one, right? On the drawing, we showed that the orange one passed the blue one, but that's impossible in the context of this problem, right? So a better drawing for the orange one would have been something like this, right? Like it starts at a high slope, but then it slows down. And just to finish up the drawing, so this other one, 5, 2, it starts at position 5. It has a slope of 2. So by the time it reaches the destination, it'll be at 2.5, which is about over here, I think. So let's just draw a continuous line. And even though it's kind of hard to draw a straight line here, but you can see again, these intersected as well, right? So that must mean, since all three of them intersected, that must mean that we're going to have a single car fleet, right? And that's pretty obvious when you look at a drawing. And actually, when we look closer at the drawing, we see that the orange one intersected with the green one before it intersects with the blue one. So actually, when the orange one intersects here, it's actually going to be traveling at the same rate as the green one. And you can continue with this drawing if it kind of gives you a good intuition of the problem. I just wanted to kind of show you like where I'm coming from with this problem and that I'm not just immediately jumping to the solution. But knowing kind of this idea, we can kind of get into the solution to this problem. And we can actually do it in linear time. So now you can see that I've drawn the cars and their positions in sorted order, and that makes sense, right? Wouldn't we want to go through the cars in sorted order? Because of course we know that they can't, like the relative order of the cars is never going to change. So it makes sense to go through them in sorted order. Now, for any two given cars such as these two, how do we know if they're going to intersect or, they're going to collide and become a single car fleet before they reach the destination position? Well, basically by the drawing I showed you earlier, if these two intersect each other, right? So what we could do is actually calculate the intersection point of these two if we really wanted to. But there's a slightly easier way. We can just calculate what time is this car going to reach the destination and what time is this car going to reach the destination. If this car reaches the destination before or at the same time as this one, that must mean that they became a car fleet, right? They became a car fleet somewhere in the middle, somewhere in here. So since this one is moving at 1 mile per hour and this one is moving at 2 miles per hour or whatever, whatever unit of speed or something that they gave us, we can calculate what time they're going to reach the destination. We can do it pretty easily, right? We can just take the distance difference for, I'm going to do the green one first. We can take 10 minus 7, right? That's the distance that we need to travel, 3 units of distance, and divide that by the speed, in this case 1. So this is going to reach the destination at time equals 3. We can do the same thing for this one. So 10 minus 5 divided by 2, that's going to be 2.5. So this is going to reach the destination at time 2.5. So that must mean that they are going to collide. So we know they're going to be 1.5. So this is going to reach the destination at time 2.5. So that must mean that they are going to collide. So we know they're going to be one car fleet. So technically we can kind of just like delete one of these, right? And just not consider it anymore. But which one of these two are we going to remove, right? Like, okay, let's say I remove one and then, I start comparing the remainder of the list that's on the left side. Well, I'll tell you right now, we're always going to keep the one that comes ahead because if these collided, they're going to end up being reduced down to the speed of the one that's ahead, right? So this is going to start traveling at 1 instead of 2, right? That's going to be the new speed. So if we want to know if these two intersect, it's going to be harder to calculate because this one is going to have two different. Want to know if these two intersect, it's going to be harder to calculate because this one is going to have two different speeds. Initially it's going to be 2, but at some portion it's going to change to 1. So it's easier if we be 2, but at some portion it's going to change to 1. So it's easier if we keep this one because this one is always going to be traveling at speed 1. And one more thing, we're not going to go from left to right, we're going to go from right to left when we do this operation. And the reason is pretty much the same. Because if we started at the beginning and then we were checking, okay, does this one collide with the blue one? Well, we don't even know what speed the blue one is going to be traveling throughout the whole thing. We can't just assume it's traveling at speed 2 the entire time because it could collide with somebody else and slow down. That's why it's better to start from the right and then iterate through this in reverse order. Okay, now just to complete the example, so we know that this is going to end up colliding with this one, so we can just assume that this car is a single car fleet. We have one more car over here, and it's traveling at speed 3. So now we want to know, is this one going to collide with this one? We already know what time this is going to reach the destination. Let's calculate the time this is going to reach the destination. So we can do 10 minus 3, so that's 7 divided by 3. That's going to be 2 point something, right? Let's just say 2 point, I think it's 2.3 or something, but it's not too important. But we know that this since it has a smaller time than the one ahead of it, then they are going to collide. And remember, which one of them are we going to delete? We are going to delete this one because it's the one that's behind. Okay, so before we get into the code, just to mention the overall time complexity of this portion of the algorithm where we're actually going through the cars is big O of n, but of course we know we actually have to sort the input based on the position, so that's going to make the overall time complexity end up being n log n, and the extra space is just going to be big O of n because we're going to be creating a separate array, but we're also going to be using a stack just to give you a preview of how we're going to be doing this. So just to let you know, initially our stack is going to be empty. We're going to go through this in reverse order. So first car, we're going to go ahead and add it to the stack. Okay, next car, we're going to go ahead and take this and then add it to the top of the stack. But then we're going to compare this car with the other car that's adjacent to it on the stack, right? Both of these are going to be on the stack. If they collide with each other, which we can calculate pretty easily, then we're going to remove the one that's on the top of the stack. This one is the one that's on the top. We're preview of how we're going to be doing this. So just to let you know, initially our stack is going to be empty. We're going to go through this in reverse order. So first car, we're going to go ahead and add it to the stack. Okay, next car, we're going to go ahead and take this and then add it to the top of the stack. But then we're going to compare this car with the other car that's adjacent to it on the stack, right? Both of these are going to be on the stack. If they collide with each other, which we can calculate pretty easily, then we're going to remove the one that's on the top of the stack. This one is the one that's on the top of the stack. So this is the one we're going to pop from the stack. And that's how we're going to do the algorithm. So, assuming we pop on the top of the stack, this one is the one that's on the top of the stack. So this is the one we're going to pop from the stack. And that's to it on the stack, right? Both of these are going to be on the stack. If they collide with each other, which we can calculate pretty easily, then we're going to remove the one that's on the top of the stack. This one is the one that's on the top of the stack. So this is the one we're going to pop from the stack. And that's how we're going to do the algorithm. So, assuming we pop this from the stack, but then we add this one, and then we end up popping this one as well, what we're going to end up returning is the number of car fleets that actually exist at the end of the entire algorithm, which we can get easily because we can just take the length of our stack and that'll tell us how many car fleets we actually have. And it's just going to be a single one in this example problem. So now let's get into the code. Okay, now let's write the code. I love problems like these where we can spend most of our time actually explaining it and talking about it, and then the code becomes easy. The first thing I'm going to do is just kind of create an array of
Both solution, okay? Both the approach, okay? So this approach is much more faster than the approach second, because in approach first we are creating, but overall it should be same, because we are going through that will be O of n, inserting and removing will be O of 1. So overall time complexity is same, but it's taking more time. So let's such an approach. So now let's move on to the
Of pair.
next problem. Let's move on to the next problem from stack. What's going on? Short, which is time, it's target. So position of the target station of target, that is position system. So the sort the vector, sort the vector. Time, that's it. So the answer. Right. So target minus areas position divided by speed. Okay. Then position. Stop. Just through. Position. Descending or check tested empty and and this is then stack top. Continue. This stuff. This. largest rectangle. Okay, the angle in an histogram. Okay. So let's go through. Given an array of integer heights representing the histogram bar. Okay. Represent the histogram bar height where the width of each bar is 1. Returns the area of the largest rectangle in a histogram. So that is 2, 1, 5, 6, 2. This 2, 1, 5, 6, 2, 3. So the largest rectangle will be 5, 5. How do we do this? So for this problem again, let's do it small. So the above is the histogram where the width of each bar is 1. And the largest rectangle is shown in the right area, which has an area of 10 units. So all you need to do is, like, let's start with here. So we'll calculate its histogram. That will be rectangle. That will be 1 cross 1. That is 1. Then we'll move 1. If it is smaller, let's move on to here. So I can calculate 1 plus 1. Okay. Well, we can have two variable. We can have a 2 pointers, one pointer to this and one pointer to this. Okay, one pointer to this and one pointer to here. Then we calculate. Okay, after calculating, now can I calculate the area? Then we move rectangle here. We check if it is greater. If the second pointer is greater than the rectangle, what it is, both, let's start both with 2. Then we'll move one here. So if we move one here, calculate. If it is shorter, we leave it. Then if it is larger, if it is larger than the previous, we move the right to here. Then we calculate for this itself. We can calculate it for itself too. Okay, this is 4. Let's say if it was 5, the largest histogram will be this one, 5. Okay, so we calculate for itself and the next one. So for this self, it will be 2 to 4. Then we move right pointer here. So after getting the pointer here, we'll start like this from here and here. So we'll see if which one, left pointer and right pointer. We calculate the histogram. So if you calculate the histogram with these, it will be this. So this will not be an histogram because there is a shorter one here and there is a bigger one. So let me start with this pointer and this pointer. If it is, then we will calculate for 2. Then we move one pointer here. To move the pointer here, we see if it is, then calculate pointer here. Calculate the for this one, this, and for itself, for this and for itself. Okay, so that is 1. So that means we reduced. That means previously it was 4, now it's 1. So what it is, move the pointer over here. So now let's calculate for this. So yeah, then both pointer is here. So 1 pointer here. Okay, after calculating this, if it is smaller, we move both pointer to here. Calculate for this one. That is smaller. Then again move both pointer over here. Let's see If it is 5, so it will be 5. So itself now is for it's 2 and 1 it's 5. I'll say check if 5 is greater than the result. Okay, it is greater, so it's to 5. Then we move 1, so it is again larger, so we calculate for these. So calculating for this, it is larger, we keep moving. Again we move this pointer to here, so it is smaller, we move pointer to the head. If it is larger, check for this one. So this is greater, put in 6 and I put in 5. How can we start? We have one pointer over here and another pointer over here. So what we do is, if the graph 3, 1, 5, 6, 2, and 3. So let's start to 1. So let's start to put pointers here. So what was the thing that start from here? So it's 2 and it's 1. So it's calculated and we have a result. So for result it will be 2. For starting it will be 2, because it 2 itself. Then what it is, move the pointer over here, left pointer over here. We put this pointer, remove this pointer, this pointer over here. So then again we calculate the histogram for both, that is 1. So we got a smaller, even it's 1, we got 2, it's similar, so we move. So first we check for itself, if itself is greater than the result, so it is not, then we check for both. So left minus right by smaller, so that will be 2. So we, again it's more than, so what it is, move. Move this to here and then this to here. Okay. If it is smaller, we move it's, we calculate. But if it is smaller, we can be sure if our if we start with it and we move one pointer here. So if this pointer is smaller than this one, we can be sure that this if this is smaller, we can be sure that this is not greater than the result, but this would be greater than this. I minus this would be greater. Okay. So we calculate that. We move the pointer, left pointer here, we move the black pointer, so move this pointer here and move this pointer. This pointer over here, and again we calculate, we see if this is left, right. If right itself is bigger than result, so change the result to 5. Change the result to 5. Change the result to 5. The result is 5. And again we calculate this, that will be 112. So if it is smaller, we can move the right pointer here. But if it is, if got the result bigger, so if we get the result bigger, if our right pointer is bigger 5, we change it to 5. And move the pointer over here. So we are not using any stack. So because it is a stack problem, I think we need to do it using some sort of stack, like a two-pointer problem. So how can we use this stack? Let's add 2 to the stack, then we add 1. So calculate this 2 area, both area. So 2 and then 1. 1 is smaller than 2. So we do what it is, we leave 1 as it's. Then if it is smaller, we don't add. Then we have 5. We have 5. If it is greater than this, we will remove the 2 and add the 5. Then again, if we are greater, we add this. If we add 6, we have. If it is smaller, we don't add. If we have greater than this, if we have smaller, we pop it, and we add this one. We don't add this one, but we pop the equation. If we have 6, let's say we have 5, then we add 5 to the step. Then if we have greater, then we keep add. If we have smaller, calculate area for this both. If we have smaller, we pop this one. We pop this one. Pop 6. If it is greater than this, we pop 6, pop 5, pop both of this. Then we have 2, then we're going to have 3, pop, we add 3, calculate for this one. So let's say if let's say if there was in middle, there was 2. Okay, so there, if we add 5, we have smaller than this one. So let's see what it is. Let's say there was another one here. 2. So this will be the greatest one. That will be 2, 3. 2 into 3, that will be 6. 1, 2, 3, 4. 4, that will be 8. 2 by 8. This is 5, 5. No, that will not be 8. That will be 2, 2, 2, 2. Okay, that's it. So 5 is smaller one. So if we reach here, we add 5. If we have a smaller one, what we do is simply add smaller one here. Whatever we add it to the 5. If we have greater one, we pop this one. No. Let's go to the solution again. Let's see. Let's go to the hint. That problem monotonic again, monotonic. So let's sort this one. Let's say if we sort these, monotonic is stack. So let's do 2. Calculate 4. Calculate for 2. Then calculate for 1. Monotonic is stack. So in the stack we add plus 2. Then we set 1. So 1 is smaller. We add 1. Then 5. So 5 is greater than this one, and 5 is greater than this one. So we pop both of these from the stack. So we leave the 5. Then we have, if it is smaller, we add, then we have 2, we add this. Then we have 6. We have larger than the previous thing. Monotonic, ascending order, descending order, descending order. If we have 1, if it's smaller, we pop it. 5, we have 2, so we pop this one. 5. Then we have 6. Two, that is only 6. But if you have 3, one more here, 2, let's see. So, okay. So why is this not considered like 2, 2, 2, 2, 2 to 4 to 8? So 2 to 4 to 6 to 8. That's also only 8. So 1, 2, 3, 4, 5. That's also. So how can we do this? Let's sort this. 2, 1, then 2, then 2, then 3, then 6. Okay. So if you even sort this one, position can be like 5, 6. Okay. So if you sort these, what can we do? Cannot do anything. If you sort these, we still need its positions. But where its index. So 5 at this index, this at this index. How can we compute this one? If we add it to the stack, so add it to the stack. 2, then we have 1, which is smaller. Let's pop the 2. Then what we do is smaller, we pop it, what, and pop it 5. Then again we have 6, so we add 6. If we have and if we have, let's calculate this. That will be 5 by 10. Okay. Smaller one, now the smaller one twice. So again, let's add 2. So let's pop it. So that will be 2. So 2 and its position, and its position, and its position. So we have 2 smaller one. So 2 smaller one into difference in position. So we have, let's difference in position. What is that is 1 and 2. So that is 2. So 2 into the, let's say 0, 1, 2, 3, 4. This is 4. So 4 minus 2, that is 2. So 2 to 4. Including itself, it will be 4 to 8. This will be 8. 0, 1, 2, 3, 4. So 4 minus 2, that is 2. So 2. But if you calculate itself, it will be 1 more. So for this one, if it is 5 and 1, so 1 minus 1 plus 1. This position is this position plus 1, and the smaller one. We have 3. Okay, we have 3. Then we have again, if we have greater, what do we add it, whatever the smallest one. Okay. Smallest one the smallest one into that is 4 5 5 minus 2, that is 5 minus 2, that is 3 plus 1, that is 4. So 4 into 2, that is 8. So okay, so let's do this, the logic that we currently implemented. So plus 1 plus x plus let's try to implement this one. Okay. Let's get a stack of int as a stack. Okay, so while int x let's see it's ts heights. Okay, so simply what we do is check if stack.emp if its stack is not empty, stack is not empty, and our current height is we add to our current height is smaller than our current height is smaller than the previous height. What do we do is if our current height is smaller than previous height, like if you have 2, then if you have 1, so we pop 1, then if you have 1, then if you have 5, so we pop 5. So stack, let's add int pair of int. Okay, so let's start say for the height. So we pop the pips. If it is smaller, we pop. If it is larger, we add. So once we add this one, if it is smaller, we pop and don't add itself. We need to add itself. Then we have 5. It is larger. So in 1 and 5. Then you have 6. We have larger. So what it is 1 5. This we complete this, and we have 2, which is smaller, which is larger than the smallest one. We pop this one 3, then we add this one. If it is smaller than 2, it is smaller. If we add 2, then we add 1, then we have to add 5. So 5 is greater than both of this, so we pop both of this. We add 1 2, then we have a smaller, so we pop this one. We have 1, so add another one, so add 5. If it is smaller, pop it and add itself. If it is larger, pop all the smaller one previously. So let's say if there is 2, so if I add 2, then we have 2. So if it is smaller, what do we do is pop the 5. Let's say we have 2 here, so what do we do is 5, then we pop the 5, we'll have 2, it's 6. If we pop the 5, we have 2 and 6. Then again we have smaller, we pop the 6, 3. So we do this from here to here, from here to here, but still we have 5. If it is smaller, add it. If it is smaller, we add it. If it is larger, if it is smaller, we keep on adding. Okay? Let's say we add 5, then if this one we add it. 6, let's pop this smaller one, let's pop this one, 6. We add it, we calculate it. We have 5, we add it. 5, we have 2. What it is, 2, we add it. We have 6. Pop both of these. Then again we have 2. Add it, 6, 2. We pop both of these. We cannot get these from 2 to 4. 2 to 4 to 8. The 2 to 4 to 6 to 8 to 10. So this will be 10 if there was a 2 in between. So if you have 5, okay, it is smaller, we add it. If you have greater, if it's 2, then I will calculate 2, this, that will be 2, that will be 2 to 4, 4. So is 4 greater than our previous result? No. So we have 4 greater than previously, we have 5. It's 5 here. Go through the solution. How many minutes here? 40 minutes. So if we go through this one, we have 5, then we have 2, then we have 1. So after adding 1, we compute both. We see result average. So this is 2. So we are getting 2 whatever we had. So we pop this one. And we have this. We are at 5. Then again we compute the result, that will be this is also smaller than our result. So we pop this one. Then we have 5, then 2. So compute this, so to do 4. So which is not smaller than the previous one, we can pop it. We have to add 6. So again we compute this smallest, which is 2 to 4 to 6, we don't pop. Then we add this, then we will compute. If our result is smaller than this is smaller than, if it is equal, so this is equal, so this is equal 1 1 2, so we don't pop it. Then we add this one, then we can put 1 1 2 1 3, so this is 3, so we don't pop it. If we have 5 2, so let's say this is 2, then we have 5, and compute, this is 3, so we add 3, then we add this, and which one is the smallest? So 1 2 3 4, so pop it. We keep on getting the values for it, and pop. We pop current if this is greater than 2. Let's add the result at 2. Then we add C1 is 1. Next we move to the next one. We check if this is greater than our result. So this is not greater than our result. We just move on to the next one. Let's check if this is greater than our result. As this is greater than result. So we first we add the stack. Let's add 2 to the stack, and result as a 2. Then we see 1. If we check 1 is greater than our result, no, so let's move on to the next one. If 5 is greater than our result, okay, so let's add 5. So let's add 5, which have greater than result, and pop whatever it is in. So let's pop 2. So 5 is our greater than result. So we make it result as 5. There is 6. 6 is 6 greater than our result, as it is greater than result. What do we do is simply add 6 and pop the 5. So we have 6. We pop the 5. We don't pop the pop. We added 6. Add 2. and here 5 and 6, 3, 5 and 6. Pop if you have a smaller, if it is greater, you keep on adding. We don't pop, keep on adding, then whatever comes at last top, if you have top, and if it is smaller, we don't add, if it is smaller, don't add. So if we go 2, if it is 5, 1, we don't add. It is smaller than our result, we don't add. It is greater than our result, so we change the result to, if it is greater than the result, we change the result to 5, and we add this, and we have 6. If it is greater than our result, we add it. If it is 2, we don't add it. If it is smaller than 2, don't add it. If the result is 5, then we have 6. For 6 is greater than our result, so we add the 6. And the 6, so 5 and 6. And we did not add the 2 in between. If it is smaller than our result, we have result as 2, so then we will pop itself, and we will add 5, then we have 2, so 2 is smaller than the result. 5, 5, 5, so 2 is smaller than our result. So it is pop the 5, pop the 5. We do not add it. We did not add it, neither do we pop it. F6. If it's smaller, we do not add it. If this is smaller, we do not add it. 5 and 6. If it is smaller, we do not add it. If there is 2, this. We do not add it. We do 6. Yeah, I'm going to check if it is smaller than top of the stack. We're going to add it. If it's smaller than top of the stack, we're going to add it. And let's go to the solution. Let's go through.
Let's solve LeetCode 84, largest rectangle in histogram. So we're given a bunch of bar heights, and each bar has a width of 1. We want to find out what's the largest rectangle we can get and return the area of it. So in this case, the largest has an area of 10, width of 2, height 5. Another rectangle we could get has an area 8. This one has a width of 4, height of 2. Another one has a width of 6, height 1, so area 6. There's also other rectangles we could get, but these are a few of them. So if we just draw the first 2 bars, let's see if we can notice any patterns from them. So if you look at them, the first one is bigger than the second one. That means for this rectangle of height 2, we can't extend it any farther. Once we reach this 1, we can't extend it any farther. So the biggest rectangle we could get with height 2 is just this one right here, because there's a little hole over here, so we can't push it any farther. But for this 1, we can push, since the height is 1, we can kind of extend it towards the left a little bit, right? And use the left rectangle. And since we can't extend the height 2, we can still extend the height 1, because there's nothing coming after it that'll stop us just yet. Let's look at the opposite scenario. What would happen if the 1 came before the 2? In this case, the 1 comes first, so we can keep extending it to the right. There's nothing stopping us, right? And the 2, there's nothing coming after it just yet that'll stop us. So we can actually extend this height of 2 a little farther, because there's no smaller height that comes after it. So there's no hole, right? The third case is if 2 rectangles were even right next to each other. In this case, we can also keep extending it, right? Because there's no hold. These rectangles are the same height. There's no smaller rectangle stopping them from being extended farther to the right. So this tells us that the current heights are going to be in increasing order because this 2 cannot be extended beyond this point. So we can only compute the area of height 2 from this width, and then we have to pop it, right? We can't extend it any farther, so we have to remove it from being considered. So now let's look at the case where all the heights are in increasing order. Notice how since they're all in increasing order, they can be extended to the right continuously, right? So this 1 over here can continue to be extended to the right. This 2 can be extended to the right. This 3 can be extended to the right. And this 4 can be extended to the right. None of them can be extended towards the left though, right? Because the height to the left is smaller, so they can't be extended to the left. But what would happen if we introduced a smaller height after? So if we introduced a 3 over here, that would mean that this 4 over here, it can't be extended any farther because there's a 3 coming after it. So all we can do is say, okay, these are the boundaries of height 4. Let's compute the area, which is going to be 4 in this case because the width is 1. And then we have to remove this from being considered, right? So we pop it. What if we introduce the 2 instead? Well, the same thing will happen. We can't extend this 4 any farther, right? So all we can say is these are the boundaries of it, right? We started back here, and then we extended it all the way until we got to this 2. So compute the area, and then pop it, right? Let's look at this 3 now. We can't extend this any farther either, right? Because the 2 is less than the 3. So we can say that these are the boundaries of the 3. Let's see what the area it could have contributed was. It's 6. Maybe that's the max area. We don't know yet. But we know we can't extend this 3 any farther. So we have to pop it as well. What about this 2 over here? Well, since the new height that we got is also 2, we can keep extending it. There's no reason we can't. So we will only have to pop these 2 elements, the 3 and the 4, because we can't extend them any farther because now we reached a 2. Let's look at one last example to drive this point home. So now we have a 1 over here, right? So we can't extend the 4 anymore either. So we compute the area, 4, and then remove it from consideration. Also, so the stack will contain the current heights that we are considering and will pop them from the top when we are no longer considering them. So now let's look at the algorithm. So I have a stack, and in the stack, I'm not just going to hold the index, and I'm not just going to hold the height. I'm going to hold both of them at the same time. So I'm holding the start index and the corresponding height. I'm also going to be maintaining what the max area is so far. So now let's start at the beginning of the array. We get element 2. So since there's nothing in the stack, we can't pop anything. Let's just add it. So at starting at index 0, we have a height of 2. Next, we get to index 1. There's a height of 1 over here, right? So now we're going to add the height 1 to our stack. But let's look at our stack. There's a height 1 that's at the top of the stack right now. That means that this 2, it can't be extended any farther. We reached a height that was smaller than the 2. So that means we're going to pop the 2 from the stack. But before we pop it, let's just see what's the max area we could have gotten with this 2 height. So it started at index 0, right? We can see it started at index 0, and we just reached index 1. So that's the range of the width from 0 to 1. So the width is 1, the height is 2. So that means the area is 2. So far we'll say our max area is 2 now.
And now we can pop the 2 from the stack. So what's the index of this 1? Now, well, we're currently at index 1, right? So we can say that that's the index. But I'm actually going to do it a little differently. If you look at this 2, we can actually extend this 1 all the way back because we just popped this 2. That means this 1 could have been extended back by 1. So instead of and the index we reached the 6 was at 3. That means this 5 thing. And the index we reached the 6 was at 3. That means this 5 can continue to be extended. That's why we don't have to pop the 5. Now we get to index 4. This is where the interesting stuff happens. So this at this index 4 we have a height 2. The problem is this 6 now can't go any farther. We reached a 2. So this 6, which started at index 3 over here, ended up stopping at index 4. That means its width was only 1. So we have to pop it now, but before we pop it, let's get the area that it could have made. So the width is 1, the height is 1, the height is 6. That means the area it could have made is 6. Height is 6. That means the area it could have made is 6. This is the max area that this height of 6 could have created. So we'll update our max area. 6 is greater than 2. Our max area is now 6. And let's pop this 6 from the stack. Okay, now the top of our stack is 5. But wait, 5 is greater than the 2 as well. That means this 5 can't be extended any farther. So we look at the start index of this 5, it was index 2, and we stopped it all the way at index 4. So that means its width was 2, its height is 5, so the area it created was 10. So before we pop it, let's just compute the max area that it could have created. It's 10, so we update our max area. Our max area is now 10 greater than 6, and we remember to pop this 5 from our stack. Now we look at the top of the stack, it's 1, right? 2 is greater than 1, so we don't have to pop this 1, because this 1 can continue to be extended, so we don't have to pop it, right? And what about the start index do we put for this height of 2? Can we put index 4? Well, yes, we can, but we notice that we just popped 2 elements, 6 and 5. That means this 2 can actually be extended backwards all the way to index 2, right? So instead of saying index 4 is the start value of this 2, I'm going to say index 2. Next, we reach index backwards all the way to index 2, right? So instead of saying index 4 is the start value of this 2, I'm going to say index 2. Next, we reach index 5, the last element. So this height is 3. Let's put it on our stack. We see 3 is greater than 2. That means we don't have to pop the 2 from the stack. That means that this 2 can continue to be extended. There's no need to pop it. And what about the start index of this height 3? Well, we can't extend it backwards anymore, so I'm just going to say the start index is 5. If you look, we still have 3 elements left in our stack. So what do we do with them? So we have 3 elements that we didn't end up popping from the stack. What that tells us is that we were able to extend them all the way to the end of the histogram. So we still need to compute the areas we could have created from these heights. So let's iterate through them and figure that out. So let's start at this last one. At index 5, it started and it had a height of 3. So it started at index 5 and went all the way to the end of the histogram. So that means the length of it was just 1, the end of the histogram. So that means the length of it was just 5. It started and it had a height of 3. So it started at index 5 and went all the way to the end of the histogram. So that means the length of it was just 1. The height is 3, so we can compute the area as having an area of 3, right? The height start at this last one. At index 5, it started and it had a height of 3. So it started at index 5 and went all the way to the end of the histogram. So that means the length of it was just 1. The height is 3, so we can compute the area as having an area of 3, right? Now this area of 3 is not greater than our current max of 10, so we don't update our max. Let's go to the next element in our stack. It's index 2, height 2. That means it started at index 2 over here, and it went all the way to the end of the histogram, and it had a height of 2. So that means the width was 4, the height was 2. 2 times 4 is 8. Right? Now this area of 3 is not greater than our current max of 10, so we don't update our max. Let's go to the next element in our stack. It's index 2, height 2. That means it started at index 2 over here, and it went all the way to the end of the histogram, and it had a height of 2. So that means the width was 4, the height was 2. 2 times 4 is 8, so the area it created was 8. Eight is not greater than our max area either. The max area is 10, so we don't update that. And it went all the way to the means it started at index 2 over here, and it went all the way to the end of the histogram, and it had a height of 2. So that means the width was 4, the height was 2. 2 times 4 is 8, so the area it created was 8. Eight is not greater than our max area either. The max area is 10, so we don't update the max area. The last element in our stack, index 0, height 1. That tells us it started all the way back here at index 0, and it extended all the way to the end of the histogram. So from 0 to the end is a width of 6. The height was 1, so that means the area it created was 6. This 6 is not greater than our current max area of 10 either, so that means the max area at the end is 10. So that's the result, 10. So with this algorithm, we only had to iterate through the histogram once. We had to push elements onto our stack, but we had to only push
we know it's this one is smaller because we have if this is small, so we know that length would be our this length pop this one, and we know our length, and we can move on to this one. As to push, what do we do? What do we push? What about the we don't have to push it here. So what we do is calculate it for this, and we calculate it whatever it can contribute. So it can contribute, that will be this I. Then area is equal to length, this length to breadth. It's breadth. It's breadth. Okay. Let's see if below that's area is equal to max of area pound max area. Okay, so this is then after this we pop this one. What it is start pop this one. Then we need to set it index as set its height and index as the last element that we popped.
मनलाई बनाउनलाई कल नगरे तिम्रो तिम्रो मनलाई बोली सुन्नु छैन म
If it is smaller, like we pop it, we have 2, then we added 1. So and we calculated 2, so calculate 2, then we set it as this index as previous index. Or let's say this is 2. This is smaller. We calculate this one. We set it as 3. Then again we move on to this one. We set it as 2. So the last index we popped. So last index we popped. Let's do last. Let's say the last index popped. We say I. If we enter in this one, we pop it. Before popping it, index as the first. Keep on doing this and we'll last index.
Your attitude definitely no right.
So now we have all of these elements.
मलाई तिम्रो attitude नलेको हो
Max area. So we
के मैले गर्दा केही नहुने तिमीले के गरेर थाहा छ
popped. Set.
के बोला तिमीले के बोला थाहा छ
For this we pop this one.
तिमीले के भनेको थाहा छ
We pop this one. We calculate the area for this one and calculate the area for itself.
नगरा के गर्नु त नगरा के
Area
गर्नु
for
त
both this, so 3 minus.
तिमीले मलाई के भनेको याद छ
So we calculate
जहिले भने
this
भन्यौ नि
0, 1, 2, 3, 4. 4 minus 3, that is 4 minus 3.
हिजो मैले त्यत्रो भने
4 minus
के असर भयो
3, that
तिमीलाई?
is 1. 1 into 6. Then again 4 minus 2, that is 2. So 2 into. So first we calculate 1 for this one, 2 into this one. So it is divided. We are 5, then we add 6 with 3. So it is 4 minus.
कसलाई तिमी कराएका क्या तिमी? कसलाई कराएका? मलाई भन्दैछु गर्न नपला भने मैले तिमीलाई भनिरहेको छु गर भनेर अझ मलाई
4
भन्दैछौ
minus
को सुन्नु खोज्दा तिमी?
2. 4 minus 2, that is.
म तिमी जस्तो होइन कि तिमी जस्तो होइन मलाई गर्नु मन छैन भन्छ हल्का त लाज मान
This, this.
मैले भनिरहेको छु गर भनेर अझ मलाई गर्न मन छैन भन्छौ कहिले त्यस्तो सोचेर बोल सोचेर बोल्न आउँछ
Play this instead of doing this.
सोचेर बोल्न आउँछ तिमीलाई
I dot top.
मलाई गर्न मन छैन भन्छ अझ
I. And we calculate and breadth. We calculate this. Then again for the next situation we have this I. I has 4. 4 minus.
मन परि बोल्छ मलाई गर्न मन छैन भन्छ अझ त्यस्तो निन्द्रा लागेर तर नि पर्खिरहेको थिएँ
Instead of
आउँछ कल भन्छ
this,
भनेर
we'll add.
तँ चाहिँ घर पुग्यो भनेर मेसेज गरेर अझ मलाई गर्न मन छैन भन्छौ मैले सम्झाउनु थिएँ गर्नै भनेको थिएँ
Top. That height, that is second as a zero and this second. Okay? So
गर्दाखेरि भनेन मैले तिमीले कल गर्दाखेरि
return max area. So what's this?
कस्तो घर आएको दुई मिलाएर मैले तिमीलाई कहिले मेसेज गरेर थाहा छ
Okay, so then let's just return this one. Okay?
दुई घर आए कस्तो दिमाग हो कि दुई घर आयो भन्न हल्का त लाज भएन
Then
त्यस्तो भनेको छु त्यस्तो मेसेज गरेर भनेको छु
it's going to 0. I was with them. I is less than height. And I said that was
मेसेज गरेर छैन भन दुई घर आयो भनेर लाज मान न हो सोचेर बोल न हो सोचेर गर न हो
voila. It's not empty. This. Okay, empty.
तिमी आएन भने जाऊ भनेर कस्तो मेसेज गरेर पठाएको छु तर नि मलाई गर्न मन छैन भन्छ अझ कस्तो
Second is C.
मलाई मन परि गरेको छु उसको मन मर्जी तिम्रो मन मर्जी छ क्या थाहा छ तिम्रो मन मर्जी छ
So we have
तिमीलाई जे बोल्नु छ बोल्छौ तिमी तिमीलाई जे गर्नु छ गर्छौ तिमी दुई घर आए ओहो मैले झन् त्यत्रो मेसेज गरेको छु तिमी आएन राम्रै हो नआए तिमी गएर किन भनेर छु तर पनि
which is
दुई घर गयो
why height is smaller. So height is smaller than this height is smaller than the top limit.
मलाई गर्न मन छैन भन्छ अझ मैले भनेको छु जे कुरा मैले भनेको छु त्यो मलाई गर्न मन लाग्दैन कस्तो कुरा
So we are
गर्छौ
able
तिमी
to get this one.
तिमीले जबरजस्ती भने हो तिमीले
For
जबरजस्ती गरेर
this
भने हो
one, I think I am not. We are not able to.
तिमीले जबरजस्ती मलाई गर्न लगाएका थियौ
For this one, we are not.
मैले भने हैन गर भनेर
For
अनि
this
के
one,
मलाई गर्न मन छैन भनेर त तपाईँ उसको मनमर्जी चलिरहेछ अझ
so for this one, we are
अझ
simply
सबै
able
थाहा
to.
भएको
Now,
गर्छु
for this one, we are not able to get the answer because at the end we have to make this part. Let's say if we std see out. Let's do. Let's see the size. As the size, it's not empty. At the end, we need it to be empty.
तिमीले जे नि सम्झाउनु पर्ने हो मैले जे नि सम्झाउनु पर्ने हो
So it's 2. Here also it's 2. It's 3. But in the middle of this we get the answer. But
त्यस्तो
for
दिमाग
this,
हो के काम हो त
we are
जे
not
नि
able to
सम्झाउनु
get the answer
पर्ने
at the end. After going through this, all we need to do is let's create another while
अब गर्नु नगर्नु न दिमाग छैन भने त
but stack is not empty. All we do is to calculate the area. So how do you
मलाई
calculate
गर्नु
the
मन
area?
छैन तिमीसँग सर
Simply what you do is at
यो
the
कुरा
end,
मैले भनिरहेको छु
whatever the
गर
element we
गर्छु
have in this, whatever the element we have,
के
so this is 5. So we know this 5 and at the end, so end of the index,
आज दिनु पर्ने
that will be, we have 5. For this we have from here to here, so we need to know the end. 0 1 2 3 4 5 1 6, end of the 6. So what we'll do is
एउटा सिम निकाल भनेर आएको बेलादेखि भनेको त्यो एउटा निकाले हैन
last point of first point of height, just height will be just height stuff size.
हजुर कहिले कल गर्यो रे हजुर
So last point of that will be height plus size. So while it is not
आफूले
input,
कल गरेर ल्याएको पुछ्नु
with top element. So for the top element, what do you calculate? We simply what you simply do is what is simply
कल कहिले
made
गर्यो
is simply what we're going to do. Simply what we're going to do is height. It's the last point of height into length. Last POID point of just a height minus as the top index, then int BREADTH will be as the top dot CO and the second, or this will be as the top dot first. Okay, once we have both of this, we need to calculate area. Let's get area. So int the area will be simply int area will be length is just length to details breadth. Let's do max area is equal to max of the area comma max area. Okay. So we have okay. Keep on doing this well, and then we need pop that pop whatever it is in top. Okay. So now we are able to go through the solutions. Okay. So simply first what we did go through all of this, create a stack, get the we move till the end of the stack, end of the heights, and calculate whatever we can calculate. After calculating whatever we can calculate using this one, we still have element in the stack. So if we still have element in the stack, we need to calculate the area for those elements. For those elements, what we are doing is calculate the area again here. So area for in the stack. The area left area element left in the stack. Okay. So let's so it is from this point to this point. Let's submit this one again. Yep. So now this is fine. So today we again solve two problems from the stack. Okay. So this is it for right now. We'll continue it. Continue the stream again. Using so now next stream I will try to stream read through go through the book of ray tracing in one weekend. Book I am currently reading that book. Currently reading through that book and trying to implement the solutions provided. So for that, wait for an hour or two, and then I will continue the stream again. Thank you.